Express 10 cos theta minus 3 sin theta in the form of r cos theta plus alpha, where r is bigger than 0, alpha is between 0 and 90 degrees, so alpha is in degrees. Give the exact value of r and give the value of alpha in degrees to 2dp. So we have r cos theta plus alpha. We can rewrite this as, using the addition formula, r cos theta cos alpha minus r sine theta sine alpha. And we're trying to set what we have over here equal to the 10 cos theta minus 3 sin theta. We're trying to express this in that form, so therefore what we have here, the 10 cos theta minus 3 sin theta, should be equal to this. So let's set those two things equal. 10 cos theta minus 3 sin theta, and if these two things are equal, well, first of all, we can see we have cos theta here, we have sin theta here, sin theta there. So therefore, r cos alpha will equal to 10, and r sin alpha will equal to 3. So let's write that out. We have r cos alpha is 10, and we have r sin alpha is 3. We can then divide the two things by one another. So if we do the r sin alpha is equal to 3 divided by the r cos alpha is equal to 10, we then end up with the r's cancel, tan alpha is 3 over 10, inverse tan of 3 over 10 gives us to 2dp 16.70. So alpha is 16.70. And then to work out what r is, we do the square root of these two numbers added together squared. So 10 squared plus 3 squared, which is root 109. So now we know what alpha is, now we know what r is. So our answer will then be r, which is root 109, cos theta plus alpha, which was 16.70. Okay, on to part B. The height above the ground, h meters, of a passenger on a Ferris wheel t minutes after the wheel starts turning is modeled by this equation here. So let's take mental note of the units. H is in meters, t is in minutes. We're told that a is a constant. Figure 3 shows the graph of h against t for 2 complete cycles of the wheel. Given that the initial height of the passenger above the ground is 1 meter, find a complete equation for the model. Alright, so let's rewrite this equation. So we have h is equal to a minus 10 cos ATT plus 3 sine ATT. I'm going to rewrite this first of all as a minus brackets 10 cos ATT minus 3 sine ATT, because now we can see that what we have over here, 10 cos ATT minus 3 sine ATT, is the same thing as what we had here, with theta being ATT. This, the 10 cos theta minus 3 sine theta, was expressed as this. So therefore what we have in this set of square brackets can also be expressed in that way, but with the theta being ATT. So then we can rewrite this as h is equal to a minus root 109 cos ATT plus 16.70. Okay, so we want to get a complete equation for the model. We want to therefore work out what a is. We know the initial height of the passenger above the ground is 1 meter. So in other words, when t is equal to 0, initial height, so the starting height when t is 0, the height is 1. So we have a choice here. We can put this into the equation that we have here, or the equation that we have here. It probably makes more sense in this question to put it into this one, because when we put t is equal to 0 into cos ATT and sin ATT, we get exact values, whereas if we were to put it into this, we'll get some kind of decimal. So we'd be doing cos of 16.7, t would be 0, so ATT would be 0, cos of 16.7 is some kind of decimal, or it would be unless you save the full angle in your calculator. So it's probably easier to use this equation here. Let's put in t is equal to 0, h is equal to 1 into that. that becomes then 1 is equal to a minus, so cos of 0 is equal to 1, so that'll be a minus 10, and sine of 0 is equal to 0, so plus 0. A is then equal to 11. So h then becomes 11, and I'll use this version of the equation over here. That's probably going to be more useful as we go along. Root 109 cos ATT plus 16.70. And so for B part 2, hence find the maximum height of the passenger above the ground. So let's have a look at the equation that we have over here. We want to find the maximum height. So to do so, we want to think about the range of cos. A cos graph goes between 1 and minus 1. So therefore this value here also ranges between 1 and minus 1. So we want to make 11 minus root 109 times that cos as big as possible. If cos of this were therefore equal to minus 1, that effectively turns this into a plus, and that will then make h as big as it possibly can be. So when cos of ATT plus 16.7 is equal to minus 1, then h will equal to 11 plus root 109, which is our maximum height. And then for C, find the time taken to the nearest second for the passenger to reach the maximum height on the second cycle. So we identified from the previous part, from part 2, that maximum height is reached when cos of this is equal to minus 1. That's when the height becomes 11 plus root 109, which is our maximum height. That's when cos is equal to minus 1. So for question C, or for part C, we are solving cos of ATT plus 16.7 is equal to minus 1, and from this we are finding the second time at which the passenger is at maximum height. So t is time, therefore we know that time must be greater than or equal to 0. If we times that by 80, both sides, if we add 16.7 then to both sides, we get this. If we do the inverse cos of minus 1, we get ATT plus 16.7 is equal to 180 degrees. And if we think of a cos graph repeats every 360 degrees, so we can add or subtract 360 to this to get the other values. We know that ATT plus 16.7 must be bigger than 16.7, or greater than or equal to 16.7, and therefore we won't be taking away 360, we'd add 360 to get the next value, which would be 540, and we can keep on doing that. So if we now rearrange for t, so take away 16.7 from both of these values and then divide both of those values by 80, we get 2.04125 and 6.54125. So these are our first two times at which the passenger is at maximum height. We want the second time, so we're going to be looking at this one here. It says in the question it wants it to the nearest second. T is in minutes, remember, as it says over here. So then we would do the 6.54125, take away 6 to give 0.54125. This gives us the fraction of a minute that we have, times that by 60, and we end up with 32 seconds rounded to the nearest second. And so our answer would then be 6 minutes and 32 seconds. It is decided that to increase profits, the speed of the wheel is to be increased. How would you adapt the equation of the model to reflect this increase in speed? Okay, so let's have a look at our equation. Our equation was what we have over here. We want to change this equation in such a way to increase the speed. If we are increasing the speed, then what's happening to the graph is it is squishing horizontally. So it'll end up looking something like rough sketch, like this, for instance. So same amplitude, it's still going up and down the same height, just faster, so it'll be squished horizontally, the time period will be lower. So going back to our equation, let's think about the transformations that have occurred to a cos graph to make our graph a height this. So let's start from the inside, what's next to the t, work our way out. So the ATT that we have here is a stretch. It's a horizontal stretch parallel to the x-axis, scale factor of 1 over 80. The plus 16.7 will be a shift towards the left, horizontally. The root 109, that will multiply all of the y coordinates by root 109, so it's a stretch vertically. The minus sign is a reflection in the x-axis, and the 11 is a vertical shift of 11. All of the y coordinates have had 11 added to them. So out of those transformations, what affects the horizontal stretch is the 80. So if you were to have, let's say, f of 2x, that is a stretch scale factor of 1 over 2 parallel to the x-axis, which is basically a compression. If you want to increase the amount of that compression, we increase this number here. If that were 4, it'll be a stretch scale factor a quarter parallel to the x-axis, so it'll be compressed 4 times smaller than what it was to start with. In our case, we want to increase that 80. Going back to the equation that we have over here, we want to increase this 80. That will increase the horizontal compression, which will decrease the time period and therefore increase the speed of the wheel. So increase the 80 in the equation. For those who do physics, if you consider the oscillation equation x is equal to a cos omega t, omega is the angular frequency. The equation that we have here is an altered version of the equation that we have here. We have some kind of phase shift over here. We also have this 11 that shifts everything up vertically, but it's in the same family of equations. And the 80 that we have here is the angular frequency. In this equation here, it's in degrees rather than radians. If you increase the angular frequency, the oscillation happens faster. It's the same thing here. If we increase the 80, the rotation happens faster.